last time the microphone did not work, so if ever that happens again, please tell me, because then otherwise the sound is not on the video. So today we're going to pick up where we left last time. I think we were seeing this. What's going on? Yeah, we were seeing this example of computing the first order derivative for a linear function. And it turns out that if we have a matrix that multiplies a vector, then the Jacobian is actually the constant matrix that is multiplying that input vector. So the question then is, how do we apply chain rule in the case where we have two vector-valued functions? Okay. So we have one function g that is first applied on the input, and then we have another function f which is applied on the output of the first function. So when we have something like that, in English we say often that f after g, which is very explicit. So f is applied after we have applied g. You can also say f round g, which is the name of the operator, the composition operator between two functions. And so chain rule is all about computing first order derivatives of the compositions of two functions. And we talked about this last week in the case of having unidimensional functions, so functions that map from one single scalar to another scalar. Okay, so now we are considering the case where we have two multidimensional functions, so they map vectors to vectors. And in this case, they map input vectors of size n, so the first one, the one that is first applied on the input, to vectors of size k, and then f maps vectors of size k to vectors of size m. So what do you think is going to be the dimensionality of the Jacobian here? Yeah? M times what? What? N times M. Okay, yeah. So it's actually, so here it's actually going to be m times n. So it relates the input and the output of the overall function and doesn't care about what k is, right? K is going to be factored in. And there's always I'm just going to come back to that. So there's always a little bit of ambiguity when we talk about the gradient and the derivative of a function. So depending on where you read, I already said that last time, but I'm just going to say it again. So depending on the type of manuscript that you're reading, or author that you're reading, the gradient will be either row or column. So that really depends on the author. Because here we're following a book that you should have downloaded by now. The gradient in this book is a row vector, and that corresponds exactly to the definition of what the differential is. So row vector. In some other books, you have a difference between the vector. Well, so the gradient, which is a vector and is a column vector, and then the differential, which is a row vector. The Jacobian is always the stack of the differentials. So stack of row vectors where you're considering individual functions that map the vector, the input vector, to a scalar. And then, so on each row, the Jacobian will have the differential. So how that elementary function changes in the first order on each row of the matrix of the Jacobian matrix. Okay? So what you have is that you have a row per output dimension of the function, and then you have a column per input dimension of the function. That is always the case. I mean, there's usually no ambiguity there. The thing is that when in this, what's nice about having differentials being mapped to gradient vectors, row gradient vectors, is that there's no, so there's a, so you could say like the Jacobian of a vector valued function that maps to the scalars is going to be exactly the definition of the Jacobian. So there's no difference between the gradient and the Jacobian somehow. The Jacobian is just a generalization to multi-dimensions, but if I have a function that maps from Rn to a scalar to R, then I will have a row vector which maps like really nicely to the definition of the Jacobian. So that's why some authors use it like that. The other thing to have the gradient a column vector is actually usually more like in the fields that we are actually doing in optimization and so on. It's often used, and it's because then the input vector is a row vector, is a column vector, sorry. And if you have the gradient a column vector, then when you're optimizing them and you are adding gradients to the input vector, you have the same dimensionality. Okay, so very important formula here. The chain rule, when we are in this multidimensional case, is the product of two Jacobians. It's the product of the first function, and that's just the classic Jacobian here. So it's the Jacobian of G with respect to the input vector. And then we have something a little bit more tricky here, which is the Jacobian of F evaluated at G of X. So this you have to see that the Jacobian of a function varies depending on where it is being not in the example that we saw. So the linear function that we just saw, the Jacobian is constant throughout the entire domain. But for most functions, the Jacobian changes in the domain. And so depending where you evaluate the Jacobian, you will get a different value for the Jacobian. And this is what this is suggesting here. So when you have multi-valued functions, then you have to evaluate the Jacobian at that point, at the output of G, where you're considering the differential of H. So this is just a generalization of the one-dimensional case. And you see that it's just the functions of the Jacobians now. So let's take an example. So we have two functions. So this is like kind of classic physics things where you have a function that is function of a state. And then you have some kind of time law. So that takes a scalar as input and outputs how this will influence the state. And then we want to know what is the differential with respect to that scalar parameter t. So we're going to compute the Jacobian of the first function and then the Jacobian of the second function. Turns out that here the first function maps from two inputs to a scalar. So we're going to have a vector, a gradient, a row vector. And the second one maps from a scalar to two outputs. So we are going to have a vector. So a column vector. Okay, so that's the shape of the two Jacobians, which here are actually vectors. So we have, so the first one where, so if I take my analogy to states, So it's the function derivative with respect to the state, and then the second one is the kind of state derivative with respect to t, which you could call that time. You compute the analytical solution for the first vector, the analytical solution for the second vector, so you can check that out. There's nothing crazy about that. And then you compute the dot product between these two vectors, because we have a row and a column vector, so it's just like having, well, a dot product here. And yeah, so that's what you get. But yeah, so these, in the general case, these two entities here are Jacobians. So they can be matrices of arbitrary dimensions, and K can have an arbitrary size. Okay, so now we're going to take an example of computing the gradient of a least square problem. So I said multiple times, least square problems in intelligent systems are super important because they are, well, so they are the root of linear regression. So linear regression is really a least square problem. And also other things like, for example, in robotics, inverse kinematics. And in computer vision, when you're registering points, you're also doing some kind of least square problem. So like, for example, when we saw the Kalman filter in the intro lecture, and we went quite quickly over that, but the idea is that you have a measurement matrix, which tells you if I have a certain state, what would I observe as a measurement? And it's a linear matrix. Well, it's a linear relationship, so it's just a matrix. And often it's actually constant. So it tells you how the state linearly combines in order to produce some kind of measurement. And the Kalman gain, what the Kalman gain is doing, if you're looking at zero noise in the process, is just doing the pseudo-inverse of the measurement matrix, which is basically solving the least square problem of like so the pseudo-inverse is an inverse that inverts in the least square sense. So because there's no exact, so we saw this with these rectangular matrices and so on, that when we have a system of equation that is not, that doesn't end up being modeled by a squared matrix, there may be no solution, and so the pseudo-inverse, what the pseudo-inverse does is orthogonally project from the input space, or whatever, from the input space, well, actually I think it's from the codomain, to see what would be the solution, what is the closest solution in the domain. So that's the inverse, it's the pseudo-inverse, it's this orthogonal projection. And so in that sense, in the Kalman filter, which is one of the basic kind of things that is used a lot in computer vision, what you do is you compute what is the most likely state, so the orthogonal projection of the measurement on the state space, onto the state space. What is the closest possible state that this measurement could lead to, okay? So least square problems are found in machine learning. They are at the root of linear regression. They are found in robotics, inverse kinematics, and they are found in kind of perception, computer vision things, at least in the Kalman filter, as I just explained. So super important stuff. So let's consider the objective that linear regression is actually trying to solve, or the least square objective. So here we have linear least square. So least square simply means that we have this, we are trying to minimize the square norm between whatever is the target and some functions of the parameters. When we say linearly squares, it means that there's a linear relationship between the parameters, here are called theta, and the matrix here, and the function. So yeah, well, no, sorry, and the output, right? So there's a linear relationship between the parameters and the output, and this linear relationship is through the matrix phi. Okay. So how would we optimize that? Since this is super important, we should have an idea how do we optimize linear least squares, unconstrained like that. We can do it in many, many different ways, depending on the size of the components here of theta, y, and phi. But just give me one way. Yeah? So how would we optimize this objective here? How would we solve a linear least square problem? Actually, we are looking for theta. And how do we find theta such that this is minimum? There's no epsilon here. So here we just have a function, and we are trying to, the goal of linear least squares problems is to find the parameterization of the function here such that it minimizes the square distance to the target y's, the target y. Yeah? Yeah, we would compute the derivative with respect to theta, no matter what. And then, depending on the size of the problem, we might then use different ways of optimizing. So there's a closed form solution to least square problems. So we might just compute the closed form solution and use that to extract theta. And the closed form solution is the pseudo-inverse. Or if the problem is too big for computing the closed form solution, we might just compute the gradient and then do some kind of gradient descent type of scheme. So no matter what, we kind of have to get an idea of what is the gradient of that objective here. And the gradient we can compute by chain rule. So the idea is we have to identify two functions, and to simplify the problem, I mean, you do this in high school, this is nothing new. When you have a complicated function for which you want to compute or functional for which you want to compute the gradient, you try to identify how it's the product of kind of nested functions, and how you can apply chain rule, maybe the product rule, the sum rule, and these things in order to compute the analytical gradient. So here, the idea is to apply chain rule. So first, the first function we identify is that there's the square norm. And the square norm can just be like expressed with vectors like that, expressed as the dot product of the input vector. And we can compute the gradient of that. And so the gradient of that is simply going to be, so here again, we define the gradient as a row vector. So that transpose here says that the gradient is actually a row version of the column vector, which is an E, is a column vector, and we transpose that to have it in the vector form, in the gradient form. Okay. And we pose that we have a function g, this should be bold, I guess. So g of theta is a vector, and this is the inner part of the function here. And what would be the gradient of g with respect to theta? Minus phi, yes. So, yeah. And then we put everything together, and we have the following. So we have that the gradient of the overall objective with respect to theta is the product of the two Jacobians. So remember that I said that an important thing is that the gradient of the first function, or the one that is applied after g, is the gradient evaluated at a certain point, and that point is g of theta. But here, again, we have the case where the gradient of that with respect to the input does not change depending on where we evaluate it on the domain. Is this true? No, it's not. No, sorry. It does depend on where we evaluate it on the domain, but so here we replace E by this, no, sorry. E, yeah, by this thing here, and here we have theta that appears. And so depending on where we evaluate the gradient here of L theta, we have a different value. And that because that value is dictated by the value of theta directly inside here. Okay? So we evaluated at g theta. We evaluate f e at g theta, and theta appears here, and so that will change the, yeah. Okay. Not so complicated actually in this case. Okay, so now we have the gradient. How do we get the closed form solution from that gradient? You remember what a closed form solution is? What is a closed form solution? Yeah. And when we say closed form solution, we mean what would not be a closed form solution then, for example? Yeah, that's true. So, like, for example, if we have a solution that is defined as the limit of something, like when something tends to infinity, or if we have a sum, and the sum has to go to infinity to satisfy exactly the solution, we don't call that a closed form solution. Generally, a closed form solution does not imply like sums or limits or things like that. And also, and definitely not like, okay, the solution to this problem is the minimum of something, because this implies that you have to optimize something to find the solution, and the closed form solution should not be like that. It usually only implies like plus, minus, sine, cosine, whatever functions that we know exactly, and no limits. So what would be the closed form solution of the least square problem? least square means we are minimizing the square, so we are the least square problem is the minimum of that guy for theta. So it means that we are given y and we are given phi. What is then the solution of the least square problem? What is the theta that minimizes the square distance between those guys? Yeah? Yeah, exactly. So here we have the gradient of that guy, and that guy turns out is a convex function. We'll talk about convexity at the end of the series, but the idea is that there's only one minimum to the function. That's the basic idea of what convexity means in this case. So if you're talking about convexity kind of in the other case, then it means there's only one maximum, but usually we're talking about convexity in terms of minimum. So it means that if we find the point for which the gradient vanishes on the domain, we have found the global minimum, and so we have solved our problem. And so the only thing we need to do is compute the gradient and set the gradient to 0. And what would be the solution then? So first, what would be the outcome of setting the gradient to 0? It actually has a name, because, I mean, least square problems, as I said, are very central to all sorts of stuff. So even along the way, we have names for all the steps. We already saw that. So like, if I set the gradient to 0, I'm going to be left with something. Like, I'm going to have an equation, so there's going to be 0 on this side, and that actually has a name. I think these are called the general equations. And then solving the solution to the general equations is the pseudo-inverse of the matrix. Okay. But actually, it's not exactly the pseudo-inverse, it's the pseudo-inverse times y, right? So it's the pseudo-inverse of phi, and we multiply it by y. So what we are doing when we do this is orthogonally projecting y onto the column space of phi. So it's so the column space is the vector space that is generated by the columns of phi. So what vectors are possibly expressed by linearly combining the columns of phi, and we are orthogonally projecting y onto that vector space. That's what the pseudo-inverse, that's what multiplying a vector by the pseudo-inverse does, is orthogonally projecting onto that column space. All right. So you will hear that the Kalman filter, for example, is optimal. It's an optimal observer or whatever. And that's what that means. It means that it selects the state that is closest to what the measurements are providing in a least squared way. All right, so let's move on. So the matrix versions of the first order derivatives are also interesting, but they result in multidimensional tensors, and they are difficult to deal with. So if you have a scalar, that's what you all know from high school. So a scalar, or even, I don't know, from university, but whatever. Scalar function, that would be just the tangent coefficient here. What we were just talking about, so the gradient is, the output is a vector. No, sorry, the gradient is, the output is a scalar, but the input is a vector, and so that's the kind of things that we have. It's a vector. And the kind of most difficult case is kind of this case where we are differentiating a matrix with respect to an input matrix. So how do we do this? Practically, we can do it in two different ways. So here, we are taking the example of a matrix being differentiated by a vector, and the matrix has the shape 4 times 2, and the vector has the shape 3. So the first approach we can use is to differentiate the matrix with respect to a single scalar, and that's not too hard, and it results in matrices that are exactly the dimension of the matrix that we're differentiating. So here, in this case, the matrix is function of x1, x2, x3. So we first compute the partial derivatives with respect to x1, and the partial derivatives with respect to x2. And remember, so when we are differentiating in partial derivatives way, it means that all the other input variables are considered as constant. So if you end up having, like, for example, a sum with respect, so you're differentiating, you're computing the partial derivative with respect to x1, and you have a sum term that involves only x2, all that vanishes out of the equation. So this is not too hard to do, and you have 3 matrices, and then you collocate them into a single tensor, where you have these 3 matrices so a tensor in this case, you can picture it as a rectangular, a 3D kind of rectangular thing. So you have each matrix is kind of stacked with the other, and that's your tensor. I guess you all heard about TensorFlow, and this is the whole idea that basically you differentiate kind of high-dimensional inputs with respect to other high-dimensional inputs, and it means that you have kind of these high-dimensional arrays that are kind of flowing around the computational graph. So then the second approach, which is usually more desirable, and that's why we have this comment, I put this comment here, is that you can reshape the matrix function such that it's a vector-valued function, and then you just use the same machinery that we are using for computing the first-order derivative of vector-valued function, meaning like this product of Jacobians. When we have chain rule, you can then compute the Jacobian, which will be a matrix, and then reshape the first order, so the Jacobian of that function here, such that it has the proper tensor shape. So it is, often desirable to use the second approach when applying chain rule. So here we're going to take an example of the gradient of a vector with respect to some matrix. Back to a linear case. But now so this is the exact same case, as the case before. So we have matrix, constant matrix. So we have the same function, but instead of having the input be, let's see. We want to have the differential with respect to the matrix instead of having it with respect to the vector as we did before. So when we did with respect to the vector, we ended up having a Jacobian matrix which was A, And now we're going to have something different. Oops. So we have that, by definition, we define the Jacobian in this way, where we have, for each output, we have a first-order derivative with respect to the input. So here we are considering A as the input. And we have them collocated like that in the Jacobian. But here what we have is that each first-order derivative of each elementary function is going to be itself a matrix. So what we have is that if we consider Fi's, meaning the dot product between the input vector, well, so let's not be confused, so this is f of x, so I call that the input vector, but let's not call that the input vector, just x. And a row of the matrix, so this is the row index, and this is saying that it's taking all the columns of the matrix for that row index here, I. So this is a dot product, and so this is the expression of the dot product between that row of the matrix and that column vector x. And we are iterating through J, so all the component of x and all the column indices of the matrix here. So if we take the first order derivative of f of I, so any one of these kind of dot products with respect to the coefficient of the matrix for a given row, we'll see that this gives us xq, which is x at a certain index. So what we have is that when we are considering the Jacobian or gradient of these elementary function with respect to a row of the matrix, the gradient will be x. So this is kind of obvious, right? You have a dot product between a row of the matrix and the vector itself, and you're trying to see what would be the gradient of that function. So that it's a gradient because it's operating a dot product, and so the output is a scalar. And yeah, so that's x. And then if you are considering any other row for which you're not multiplying the vector, so these Fi's are these dot products for every row. And if you're considering the derivative with respect to the other rows, then this would be 0 because it's the partial derivative. And so what you have is that the Fi's the derivative of Fi's with respect to the full matrix are going to be these sparse matrices where you're only going to have a column vector which is x at this particular index at which you're considering the function. And so, yeah, and you actually have to transpose that. But so the total, so this is only Fi. So the total derivative is going to be a bunch of these matrices where x is going to move around. So x is actually at the ith position. And you're going to have one such matrix here, one such matrix here where x moved around, but it's also sparse, and so on up until the nth matrix. So yeah, this is how you do it for these high-dimensional kind of cases or complicated cases. You try to boil it down to an elementary function for which it's easy to compute the gradient, and then you kind of pack everything back together, back to the tensor. Okay. Yeah. So another way to do it, of course, is to have in mind identities which you use to compute vector-valued gradients. So the thing that we saw that was coming up first was the dot product. So if you have the dot product between an input vector and some constant vector, and you're trying to compute the partial derivative of that, this is actually the gradient of that is A here. So if you're considering the gradient as a column vector, this would just be A. Because we are considering gradients as raw vectors, then this is A transpose. Watch that the gradient, so the dot product, the gradient of the dot product is completely symmetric. So if you have A transpose X or X transpose A, in both cases, the gradient will be A transpose. So here, yeah, this is another identity. So and you can check that out on your own time. This one is quite important. So, because we often want to have the gradient of some quadratic functions, where this would be one of the terms. And it turns out that you would think, this is a second order term, so the gradient of that should be X transpose times B, or 2 times X transpose times B. But no, so it's actually B plus B transpose, which is symmetrizing B. Okay? So a symmetric matrix is a matrix that's equal to its transpose, and you can check that B plus B transpose is equal to its transpose. Yeah, so that's usually a non-intuitive fact, and it's quite important to know it. This identity also comes up a lot. This was an identity that's used in computing like pseudo-inverses. Transpose and an inverse identity here. Okay, so you can look at that when you do exercises and so on. So, automatic differentiation. Where are we on time? Yeah, so who heard already about automatic differentiation? Not really? Okay. So what we're gonna talk about now is very important for machine learning in general, but it's also very important to understand just the fundamentals of what it is. So you could say, so machine learning is basically optimizing these kinds of least square objectives where the function is not linear. Instead, it's highly nonlinear and has a lot of parameters. But apart from that, it's basically these kinds of least square objectives. So you're basically trying to, at least when you're doing supervised machine learning, and then the thing is that supervised machine learning is usually a kind of inner loop process of reinforcement learning or other types of learning. So what you're doing is you're computing a data set. So what should the system do in such and such and such cases? And then you're trying to find a mapping, a nonlinear mapping that will allow you to produce these outputs. And you do that by minimizing a least square objective usually. And so the heart of machine learning is to basically allow to define all sorts of weird functions, so mapping from the input to the output, that will induce other kinds of bias and so on due to the structure of the mapping. But then you need to optimize it. And to optimize it, you need the gradient with respect to the parameters. of the objective, and the whole way to do that is to do it through automatic differentiation. Because I guess you all heard about backpropagation, but backpropagation is just a particular way of doing automatic differentiation, so that's what we're going to see today. So generally, yes, in machine learning, we're optimizing the loss function. That's kind of what happens there, and for that, we need gradients. In robotics, we're optimizing usually cost functions. So if you're trying to make the best decision as a robotic agent, you're modeling the world. Maybe you have a notion of the dynamics, how the worlds evolve. Then you're trying to find some kind of behavior, some kind of trajectory or policy that minimizes the cost of your actions. And in computer vision, you usually have some kind of reconstruction objective that you're trying to optimize. So yeah, optimization is at the heart of all the intelligent systems. And for that, they need to compute gradients. So the thing that we're going to see is, what we just saw actually, is the least square objective, which is this here. And we saw that we can compute an analytical version of the gradient, which is only function of the data. Well, this would be, in the case of least squares, where we are trying to just find a linear fit to the data. Phi would be the data matrix. Yeah, so that's just applying. We saw how this is actually just applying chain rule, right? So we identified two functions. We identified the inner functions as G, and we identified the outer function as F. And we said, okay, so this is F after G, and we're going to compute the gradient of G, we're going to compute the gradient of F, and then we're going to compose them together, and this led to this gradient here. But what do we do when F is too complicated to proceed by just a simple, by having closed form solution, by just identifying maybe 2 or 3 composition and then computing the analytical closed form solution? So what we do there in practice is doing backpropagation, and the only thing that it's doing is computing the gradient efficiently by backpropagating backpropagating the gradient from the output to the input, and kind of like storing the computations along the way, such that they don't have to be recomputed. So that's what backpropagation does. And let's see just a feed-forward network. But before we see that, I just wanted to say a few things. So yeah, so the example of a deep network, of course, is a convolutional neural network that is mapping images which are maybe, as we saw, matrices are also vector space, so you can just consider, and we can just reshape matrices such that they are vectors. So let's call that these image vectors to the vector class Y, okay? So in deep networks, chain rule is super important, and it's actually used to an extreme. So let's say we have not only the composition of 2 functions, but we have the composition of k functions. So fk after fk minus 1, blah, fk after f1. So yeah, we are taking the input, applying a certain function, then applying another function on the output, and so on and so on and so on and so forth. And then we get y. So every function fi possesses its own parameters. That's the notion of these networks. And we can kind of draw it like that. So we get an input vector, which, as I said, can be a vector representation of an image. We have 2 parameters here, A0 and B. B is often called a bias. That's why we split it. Maybe you've heard about the weights and biases framework for machine learning. So it comes from there. So these are the weights of the layer, and this is the bias associated to the layer. And the goal of any machine learning engineer is going to be to work out through the weights and biases of its model, the best predictive model. So the model that can, given, for instance, an image as input, can best predict the classification of what object is actually represented in the image. That's one example of a machine learning task that is very popular. So yeah, so the network just composes the input layer with another function, and that so on and so on and so on and so on until you get the output class here. So the key thing in machine learning is that then we're going to have a least square objective, for instance. So if it's maybe a classification task, we might have another type of objective, maybe cross-entropy objective or something like that. But it doesn't really matter. So here we are just saying we have a loss function, which is maybe comparing on our training set how well we are performing with respect to some metric which is not so important for our case here. So in a neural network, these f's will have a particular shape, so they will basically be a linear function of the input, actually an affine function because we have this bias here, an affine function of the input, where we then apply something called an activation function, which is a nonlinear function. But nonlinear, of course, doesn't mean that the gradient is not defined. Actually, the gradient has to be defined, and usually an activation function has to be also monotone, meaning it increases. It's usually a scalar function. So this yeah, so these are i's. So these are like a set of nonlinear functions that are applied to each output of the affine function here. And then we apply the loss function. So like, for example, a mean squared error here, least squared error or least square objective. And we define theta now as being the combination or the set of all the weights and biases found in the network. Okay? And so what we are looking for is the best combination of weights and biases such that we minimize the least squared objective. And so we need to compute, again, the gradient with respect to the loss, the gradient of the loss with respect to the parameters. And we are going to do this using, of course, chain rule. So the key insight for these deep networks is to say that when we are computing chain rule through the network, what we can do is reuse parts of the computation, and because we have a functional, so you see, this is a scalar. This quantity here is a scalar. That's what's really crazy, right? So even if you have an ImageNet data set, so thousands of images with thousands of labels, the objective that you're optimizing is a functional, meaning that you crunch everything down to a single scalar and you optimize that function. So because of that structure, that everything is boiled down to a single number, the function network that that is defined by the loss is very pyramidal. So it takes like many inputs, but then eventually boils it down to a single output. And when any function network has this form, then backpropagation is the most efficient way of computing the gradient. And so that's why the best way is to proceed backwards. So we can call for every single layer theta j the set of weights and biases. And any layer, at any layer, the derivative of the loss with respect to the parameters of that layer is only a function of two things. First, the derivative with respect to the layer parameters, so these guys, the blue guys, and the derivative with respect to the upper layer with respect to the input. Okay, so we're going to proceed backwards from the loss all the way backward to the input. And the way we do this, so we're starting here, is by looking at what is the derivative of the loss with respect to these weights and biases of the last layer. And this is chain rule. So remember, we are multiplying two Jacobians together, or two first-order derivatives. So we are multiplying the derivative of the loss with respect to the loss input, which is so this guy, so derivative of the upper layer with respect to the input, so this is this guy, and then the derivative of fk with respect to its own parameters. So that's the first part here. Then we want to compute the derivative of the loss with respect to theta k minus 2, which are these guys. So these are all partial derivatives, and we are computing always the derivative of the loss, the final part, with respect to some of these parameters, and then we go down. And what we see is that it's still the derivative of the loss with respect to the input of the loss, which is just fk, times the derivative of fk with respect to fk minus 1. So this is the derivative of the node fk with respect to its inputs. This is what's so the derivative of the upper layer with respect to the inputs times the derivative of the fk layer with respect to its parameters. So how do we see that? So so when we're here, the idea is that we are looking at what is the derivative of the loss with respect to these parameters here. And we have the composition between three things at that point, between fk minus 1, fk, and L. And we are computing the partial derivatives with respect to these parameters here. And so that's why it's not directly dependent on the on these parameters here. Well, hopefully, yeah. Okay, so then when we arrive at this layer, at deeper layers, what we have is that we have the derivative of each layer with respect to its input, and these are summed together. And then at the end, what we have is the derivative of the layer that we're considering with respect to its parameters. Okay? And so what you see is that you can basically store all of these red parts. You can reuse all of these red parts, which are the derivative of the, yeah? Sorry, what? Yeah. Yes, I think that's a typo. So you mean there should be one here? I think that's a typo, yeah. Yeah. Because if I don't write it down, I will forget it. So. Mm. Okay. Yes, so as I said, backpropagation is a special case of automatic differentiation. We apply chain rule, and then we store the derivative of each layer with respect to the input of the layer. Also, so the derivative of the output of that layer with respect to its inputs, and not with respect to the parameters. And yeah, it works by defining elementary operations, such as cosine, sine, exponential, and all that stuff, and having analytical gradient for each of those. Those are called operators generally, and yeah, it applies to general functions as defined by computer programs as well, like if you have if-else things like that. So if we have the composition of three things, so if we have y after b after a, we can represent it by a graph like that. And so what we're going to talk about now is that we can apply chain rule in two different ways. We can apply it in the reverse mode, which is just what we saw. So you first compute this part of chain rule, and then you compute the total derivative. Or you can also go from the input towards the output, and this would be called the forward way of computing the derivative. But the notion here is that is important is the notion of computational graph, which remains no matter if you're doing forward differentiation or if you're doing backward differentiation. So let's take an example. So you have a function here that takes only a scalar as input and computes x squared plus exponential x squared and computes the square root of that. And then the cosine here computes x squared again plus exponential of x squared again. So you can see that you have 2 times the same expression here. So the question is, how would we reuse intermediate results? So if we have such a graph here, you see that there's a branch so first you can reuse the computation of x squared and propagate it forward here because you have x squared plus exponential of x squared. So maybe you can compute x squared only once and then apply exponential and then sum the thing here. So this would bring you to C, and then C you can reuse. C is this expression here. You can reuse it by having a graph like that where you branch out and you first compute the square root and then compute the cosine and then sum them up later. So what you would have here is basically operators. These are the operators and the gradient of the operators. And now the question is, how do we compute the gradient? So these operators are called G. How do we compute the gradient of F in such a computational graph? Well, we can do it by applying sum and chain rule backwards. So in the thing that we saw about backpropagating the gradient in these kind of neural networks, it was that it was a feed-forward network, right? So there was no branching out of anything, and we would just apply these things. So some rule was not implied, or was not, some rule was more like implied actually, and not really explicited there. But you have to see that every time you compute the gradient with respect to the like the operator gradient here that we just called f with respect to the parameters or f with respect to the input, inside you might be using chain rule. So in general neural networks, you might have like branching structures and things like that. And so the way that this would work is that you can do it the same way, but when you have a plus operator that defines 2 different branches, you can branch out these 2 derivatives here. Yeah, so I want to move faster because I think I want to finish this lecture today. So in the general case, if you're doing differentiation on a computational graph, you will have operators called G, and each of these operators has a bunch of parent nodes. These parent nodes are defined by the variable x with sub-indices PA for parent. So these are the parent nodes of xi, and it has a bunch of input variables and of output variables. So these parents are these inner kind of results that are computed in the computational graph. Now, you can compute backpropagation, you can write down backpropagation of the gradient as a simple algorithm in this way, or formula, which is saying that the partial derivative of f with respect to any of the input variables is going to be the sum of the chain rule applied to f with respect to all the parent nodes of f, of xi. No. With respect to all the parent nodes of that layer being defined by xj, and then you sum over all the different layers. So if you take an example here, so then you can replace this xj for the actual operators that are in the computation graph. So this is just like a systematic way of writing it down. So as an example, you would start by, you want to have the derivative of x6 with respect to the input variables x1, 2, 3. And so here d is 5, so it's all these variables here, and it includes the x4 and x5. So you first have the parents of x4, which are x1, x2, and the parents of x5, which are x3, and the parents of x6, which are x4 and x5. So if you then follow that scheme, you can compute like what would be the derivative of f with respect to any of these 1, 2, 3, or also including 4 and 5 by computing this. Okay, so yeah, so I'm going to go quickly over this. So this was for automatic differentiation. You see that the thing to remember is that when you compute it through a graph like that, there are two kinds of derivatives. There's the derivative with respect to the parameters and the derivative with respect to the input. These are two different things. But when you compute chain rule from the network, you can reuse the derivative with respect to the input for computing with respect the partial derivative with respect to some inner parameters in the network. And that's the most important thing to remember. But in general, we might want to use higher order derivatives. And just to get an intuition of why this is the case, so suppose that you want to minimize a quadratic like that. So you have a times x squared plus bx plus c, and you want to find what is the minimum with respect to x. So of course, this is again a convex function. This is again not, well, so we have a constant part here. So this is not going to play a role in the minimum. And actually, so we're interested in the argmin here. So because the minimum would be plugging that into that function. So the way we do that is by setting the gradient of that whole expression with respect to equal to 0. This was what was mentioned earlier to minimize the least square objective, compute the gradient, set it to 0, and solve for that variable. And so what we have here is that the minimizer of the quadratic here is b divided by 2a. So a is the second order derivative of the quadratic. So you can see that the reciprocal of the second order derivative of the quadratic is super important to find the exact minimum of this convex function. And so if we can generalize the Taylor series to the multidimensional case, we're going to have a similar formula for the case when this quadratic is multidimensional. And this will lead us to the algorithm called the Newton algorithm for optimization, where, of course, you cannot have a reciprocal of a matrix, but we saw what was the equivalent of the reciprocal of a matrix, which is the matrix inverse. And basically, that is what the Newton algorithm is doing. It's multiplying b here, which is the first order derivative here, times the inverse of the second order derivative. So the second order derivative is the Hessian. It is the collection of all the partial derivatives of a function f, and it is a squared matrix. When we're talking about the Hessian matrix, it's only defined for a function from a vector to a scalar, just like the gradient is only defined for the function from an input vector to a scalar. When we have higher dimensional case, then the Hessian is actually a Hessian tensor, and we're not going to talk so much about this case. Yeah. So note that the Hessian matrix is not necessarily symmetric because these things are not necessarily equal. But usually, if we're talking about the Hessian of a potential function, so the second order derivative of a potential function, this would be the case. So generally, the Hessian matrix, or the ones that we usually consider, are symmetric. So the linearization. So the first case we're going to see is kind of Taylor series of the first order. So if we are given a function f of a vector to a scalar, then the first order, the linearization of a function is very simple. The intuition is very simple. It's saying we take a point, at a point, we have a function, and we are looking for what expresses best the function around that point in terms of a line. And that's why it's called linearization. And it's the first order Taylor expansion. And the way we write that down in the multidimensional case is using the gradient here. So this is the one-dimensional case that you're all familiar with. And this is the multidimensional case. So that's a very important formula, and you should be familiar with it. So one way to see it, first set x0 to 0. Okay? Consider the point at the origin. Now, at the origin, you don't have any offset on the side, right? You don't push the function to the side, so you're at the origin. So what happens is that here you don't have anything, right? This is 0. And also what you have at the origin is that you're not offset in the upper direction here. So at the origin, if you have a function that passes the origin, the Jacobian expresses completely the function. It's the first order Taylor expansion at the origin is just the Jacobian itself, period. Now, so the rest of the Taylor expansion is saying if you're at the origin, but at the origin the function is offset from the what is this, abscissa line, or what is it called? Then you will have a term here, f of 0. And then if x0, if you're not considering x0, then you push the function to the side, and this will be this. Okay? So that's what that is. It is the linearization of a function at an arbitrary point is an affine line, right? It has an offset, and actually on top of that, it's offsetted maybe to the side. So if you consider it at the origin, but it's offset, this would be an affine line, and then it can also be offset to the side if it's not at 0. Okay. Now, we can generalize that the Taylor series for higher orders. But so first, the second order Taylor expansion has this form, so also very important to remember. Note that this is a little bit of a different expression, just to simplify things. Instead, we are looking at a point plus an offset from that point. So basically, if we look at here, we took this and we put it here. So if we would express this in the same way, we would have f of x minus delta. We'd have f of x0 plus delta. Here we'd have, here we can just remain f of x0, and there we would have the gradient times delta. So this is what we have. We have the first order Taylor expansion here. We just introduced a delta variable, but it's the same thing. We pose delta equal to x minus x0. Yeah. And this allows us to have to see the second order in this way. Okay? It's just a much more concise way of writing it. Know just that you can have like the second order be defined in this way for the general kind of RD. Oh, so no, this is the Taylor expansion, sorry. This is the Taylor expansion for RD to Rn. And you can write it concisely like this. The problem is that then you have to define delta, the kth order of delta. And so this is a bunch of tensor product of delta. Because the 0th order is a scalar. The first order is going to be a vector. The second order is going to be a matrix. And the problem is that here we are considering infinite orders. So as you move on from the second order, you're entering the tensor world. So the third order is going to be a tensor, and so on, so on, so on. And that's why this is the most concise way of writing this thing down. But it has the exact same form as when we saw it for the scalar case. Yeah. So here, but we don't have so much time. There's an example. I have an example here of computing the second order Taylor expansion of that function here at a particular point, 1, 2. So the way we would proceed is, because since it is a polynomial of the degree 3, everything after 3 will vanish. So actually the second order polynomial is not completely the polynomial itself, but it's almost the full polynomial. I know, so we wanted to compute the third order. Mononomial, I don't remember. Okay, so the idea is to get all the terms, so the mononomial terms, so the derivative of that. So some rule makes it so that you can always compute each term independently, and you can compute it for all the orders, and then sum them all together to get the Taylor expansion or the Taylor series. So for the 0th order, you just have to compute the function value for 1, 2, so that's easy. For the first order, you compute the first order derivative with respect to the two inputs, the partial derivatives with respect to the two inputs, evaluated at that particular point, 1, 2. So you first compute, what we do here is we first compute the analytical gradient with respect to, the first order derivative with respect to x, and then with respect to y, and then we evaluate it at the 1, 2 point, okay? So what we end up having is a vector, which is the evaluated vector at 1, 2. Then that gives us the first Taylor expansion term, which is the gradient. Yeah, so this is x minus x0, remember? So in the first order Taylor expansion, you have the Jacobian times x minus x0, and you also have this factorial coefficient, which I didn't talk about when I was presenting this, but so this is x minus x0, and this is the gradient. And then for the second order, we compute the second order derivatives, and this is not constant because we have this term here, which still depends on y. So we have to plug in 2 here, which ends up being 12. So here we constructed the Hessian matrix, right? That's the whole point. Then we compute the mononomial associated with the second order derivative, which is 1/2 of delta transpose times the Hessian times delta. Delta, again, is x minus x0. So we have x minus x0 here, x minus x0 here, and the Hessian matrix here. This is just vector matrix computations. And then that's the most difficult part, computing the third order. But actually, at that point, we have this weird tensor here, but most of the stuff vanishes. So we are actually just left with these two numbers. And we can put everything together, which is the 0th order derivative, the first order derivative terms, the second order derivative terms, the third order derivative terms, the sum, and that's the entire Taylor expansion. And actually, yeah, so we can check that this is the original polynomial, that basically the Taylor expansion expresses everything. And that was because we did the Taylor expansion of a third order polynomial where all the derivatives after the third order vanish, okay? Okay, so that's it. A bit late, sorry. So yeah, what we saw is that derivatives come from the difference quotient. We have closed form solutions for the derivatives of polynomial and so on. We can compute derivatives analytically using the differentiation rule. In practice, we use actually auto-differentiation in computational neural networks to compute derivatives of neural networks by applying chain rule recursively. Backpropagation is the best way to do that when we have a network or a function, a convolutional graph that collapses to a single scalar, and it does that efficiently by storing the intermediate results, especially in terms of the derivative of each node with respect to its own inputs and not the parameters. And when we have complex functions, we can approximate it using derivatives. This leads to the Taylor expansion, and that's it. Okay. You have questions? No?